Hi everybody, thanks for joining. Today we will talk about LVGL. This is the second session of the LVGL webinar. I'm Luigi Passer and I'm from the R&D team of Variscite. Let's start. This is the agenda of the webinar today. We will have a brief Variscite introduction. We will talk about the LVGL features, so a brief overview. We will go through the code analysis of the demo that we shared in the GitHub repository. We will briefly talk about the simulators and the visual editor, and we will have some time for the questions. Let's start with Variscite. Variscite is in this market since 20 years ago. We have an extensive customer base, and we have a stable pipeline in internal production facility that allow to fully control the manufacturing process. We directly support all the customer through the R&D team, usually within 24 hours. We support the customer through the customer portal and through the wiki and through the direct contact when required. We are a platinum partner of NXP, so we have very early access to the new SoCs that NXP developed. We provide an extremely diversified portfolio of IMX products, and basically you can customize all of them according to your needs. We satisfy the highest quality standard to reach also the medical standards that several of our customers require. And we can rely on an ecosystem of partners in terms of a company that can help us in the development both of the software or the hardware when we need to assist the customer that need to quickly reach the production phase. The advantages to use Variscite, we can start talking about our pin-to-pin compatibility families. We have two main families that we will show in a while, the Varsom and the Dart family. We allow a complete some customization. We have 100% yield all the time. Our hardware and software is production ready. Our hardware and software is tested by hundreds of customers, so that we can our hardware can be considered highly reliable. We provide through the customer GitHub and VariWiki free support to the customer. We also provide for the other designed CAD files, and we can provide the longevity up to 25 years through the same longevity plan that NXP can provide to us. Let's talk about the compatibility families. The big one is the Varsom. Basically, you can use the same reference board, that is the Symphony board, and plug whatever SOM you like. Of course, you need to use different software, but hardware side, it's the same. So you can switch between the 6UL, the IMX6 SOMs, the 8X, the 8 Quad, all of the 8M families, so Mini, Nano, and Plus. And nowadays also the Varsom IMX93 and the AM62 that are the last one based on TI SoC. In the Dart family, we have the Dart MX8M Plus, the Dart MX8M, and the Dart MX8M Mini. All of them share a different reference board, that is the DT8M custom board. And in the same way, you can just plug and plug whatever SOM you like, switch to the right software, and you get full compatibility other side. Now let's talk about the features of LVGL. We briefly introduced this framework in the previous webinar. Let's summarize the main features. It's an open source framework, completely written in C, but compatible with C++. It's hosted on GitHub. It's completely free under the MIT license. This allows customers to develop commercial application without any royalty fees, whatever. The main feature of this framework are based on the capability to manage basically any resolution. Basically, from the very small display, if someone of you is familiar with the SPI displays, 320 by 160, or something like this, up to the big monitors. Here we write 4K, but in the future there's no actual limitation to the size of the monitor. Also, this can be used to manage multiple displays simultaneously. There's a chance to customize the color format. There is a flexible buffering mode that allows to improve the performance while keeping low the memory usage. There's a chance to use multiple input devices, and the interfaces are quite simple. So one driver gets the state of any input device, and you can manage everything. Also, the framework allows using the gestures, so you can also manage pinch and zoom, whatever. Talking about the widgets, in the drawing feature, there are at least 30 powerful widgets. All of them are customizable with styles and whatever. The anti-aliasing features is a feature already included in the framework. You can draw rectangle with or without the radius, border with the same features. You can manage shadows, line arc polygons, and also you can mask the colors of an image through filtering, let's say, just masking. This is a quick overview of the main widgets. There are the basic widgets that are the arc, the button, the images, the label, the pen, and the text areas. There is a special widget that is the screen. This is the main widget. All of the other widgets are somehow children of this one. And this screen is strictly related to the main display, or actually to display. There can be more screen if there are more displays. There are then control widgets like the calendar, the checkbox, the color wheel, and so on. And also the visualizer widgets like bar charts and spinner. Then the customer, the user can implement his own component widgets according to his needs. Let's see some sample. For example, here we can see the arc, the button, the images. These are pre-built widgets, so you can use them out of the box. You don't need to create them. And the same apply for those widgets. So the bar, the chart, the spinner, and so on. Very useful. The keyboard, because quite often in handheld device, a keyboard is required and very useful. And about the widgets customization, let's say that the main approach is the one related to the styles. This is more or less a cross-graphical platform. Most of the graphical platform provides styles. Even in this case, there are styles that you can apply to a specific widgets, but even to more than one widget that we will see later. And you can create your own style. You can define how the widget in this element looks like and which effects can be applied to this specific object. So you can cascade the styles more or less like it happens in the HTML. You can reuse the styles for more than one widget. So you can define one and use more. And you can create your own custom local styles for simple changes, just to apply to a specific condition. You can define themes in order to have a kind of default behavior. And also you can manage transition in terms of animation between states. Let's see the main properties of these styles. We have the border styles, where you can choose the color, the width, the side. For side, I mean left, right, up and down. And the same for the line style. You can define the color, the width, the rounding of the line. If you want or not outline the colors and width. And then for the shadow, you have something similar with the color, the width, the spread that you may apply, and the offset. You can have also some padding between the objects. You have the background in terms of colors, alpha blending, the gradient if you like, the background main gradient and radius features to manage more nice visual effects. You can clip the corner. For the text, you can manage, of course, the color, the spacing between the letters, the spacing between the lines, the alignment, the decoration, and then you can also define if you want your text to be striped, to be underlined, or whatever. And of course, you can define the text font. Similarly, for the background, you can select a specific image. You can decide the opacity of this image. You can recolor the image according to your need, and you will see this specific feature during the analysis of the demo of the code, and also the image style. Let's see a quick example, a couple of examples about the styles. Here we are drawing just a simple rectangle, but we initialize the style. We define the radius, we define the background opacity and the background color. Then we add the border. I'm talking about the example on the left. Then we apply the border color, width, opacity, and on which side we want this. And finally, we create the object and apply this style. This is specifically using the border, but we can also do something similar using the shadow. So more or less it's the same, but instead of the border, we set the shadow property and we say the width and the color, and that's it. On the right, you can see what happens when applying the shadow to the same object. We can also have animation. In the previous webinar, we have seen how the images can be loaded through the tool that converted the images, usually PNG, to C code, and then you can import this C code through the LVGL declare function that you can see in the sample code. Basically, what we do here is setting the image to be used, forcing a kind of a pivot, basically a reference point to which will be applied the animation. Then we will set the animation in terms of which is the object to be animated, and this is the set var. We set the callback, so which function will be called during the refresh. We're setting the angle ranges. The angle is expressed in terms of degree, so the full range is from 0 to 3600. And then we also set the time. In how many steps we will reach the complete cycle. Finally, we define how long it will be repeated, the animation. And in this case, we simply say for infinite times. The callback here is just a set angle call that associate the rotation of a specific angle to the image. The angle comes directly from the framework and is obtained as following steps from the full range divided by the time of interactions, that is 5,000. And this is basically the main idea behind the animation in LVGL. Let's talk briefly about the parent-child structure. Basically, as I said, there is a main widget that is the screen, and all the other but the screen have a parent widget and may have children. So the screen itself will have only children, and whenever a children move within the parent area, all its own children move in the same way. So basically, let's consider the dark rectangle as the screen widget, the main one, and then a giant rectangle that is its very first child, and the giant one has a child itself that is the orange one. So if we move the giant widget within the area of the screen, then the child of the giant will move consistently, because every children is always, let's say, has always a fixed position compared to the 0, position of the parent. So the movement is always related to its parent, and the position is always relevant to its parent. If the position of the parent changes, obviously also the children will move. And let's talk about the absolute position of the objects. Basically, the structure is always organized with the coordinate 0, 0 in the upper left corner. So we can either set the position of the object setting its x value or the y value. But even in only one instruction, we can set both. So on the right, you can see the single instructions to move the x and the y value, but also the unit instruction to move the object in one shot, let's say. Whenever we change the position of an object, we also deal with the layout and the sizes. So basically, it's very useful, the relative position, set the relative position using some of these, let's say, preset value. Every object can be aligned referring the parent, and these are the references that you can see on the left. But you can also align a specific object to another object, and this is achieved with the second line of the code that you can see, the align to. When you align to the label, the button object will be aligned to the button label. In this example, we say align the button object to the label, putting it in the top mid area. So this will align these two objects relatively. But also you can specify an X and a Y offset. So in this case, we have 0 X offset and -10 as Y offset. Now let's start analyzing the code. This code is the one that we published last time at the end of the webinar we previously had. The demo code lead to this application that you can see here in the animation. And basically, we have some, you can see in the upper left side, a logo. Then on the left of the logo, there is a label. And then we have two tabs, the widget and the codes. And according to the active tab, you can see different widgets that are running. So let's try to understand the main widget that we are using to analyzing their own code. First of all, let me clarify that in the code you will find the main, that is very, very simple. The main code just initialize the framework, initialize the frame buffer, initialize the input device management, and call what we call the GUI, the graphical user interface, that is in a dedicated file. So this LVGL demo.c file can be used as a skeleton, where you can just need to change, when you write your own application, the actual graphical application that we put in an external file that we call the GUI.c. The GUI.c will be the code that is in charge to generate all the widgets, and populate the display, and then let the display refresh. Let's go step by step, starting from the style creation. As we told previously, one of the useful features of this framework is the presence of the styles. So we will create some dedicated styles for the text, for the icon, for the bullet. How can we do this? Let's start with this 4 styles. every time you want to create a style, you need to initialize it as a kind of empty style. And then you can start setting the properties of the styles. For the style text muted, we can just set the opacity, and we will see where we will use. Basically, whenever you will apply this style to a text, it will apply somehow grayed because the opacity is set to 50%. The title style will apply a large font. The font is the one that you can see in the code, the Montserrat 24, and this specific style will apply this specific font, the font large. For the icons, we will set a primary color, and we will apply also the text style as large. Finally, for the bullet, we will set the border to 0, and we will apply a specific radius to the bullet. Let's see how this will show. So let's start looking at the label beside the logo. We create the label. We set the text of the label. I'm talking about point 1. And then we align the label to the logo. As you can see, we use the align tool. So we reference the label to the logo, saying add right in the middle, applying an X offset of 10 pixels. And this is for the label in the upper side. Then we have the sliders, the free slider for the color. And you can see that we applied the slider, the style text muted to create the word red, but the same for green and blue. And so the words, the label is grayed. And we also position the label according to the position of the slider. So we use once again the align tool. We align the label to the slider, setting it in the middle at the bottom, applying an offset of 0x and 15y. This is how it works for the very first widgets that we are using. Let's now check how we can create the tabs. As you remember, we have two tabs, the widgets and the gauge. So basically, we need to create a kind of tab view. Actually, it's a dedicated API in LVGL. We start creating the logo. We create the label beside the logo, and we create the tab view beside the labels. Beside the label. So this is the architecture of the header of the application. And this will create objects for each tab that we will populate later. Let's talk about the animation. In the first tab, the widget on the left is the animation with 3 buttons: start, delete, and stop. There are 3 objects that can be that automatically move, and we have a slider. So we have the animation code. The panel contains this object. The slider will be used to move through the animation. Let's see how it works. We have a panel container that is the one associated to the tab. In the panel, we create the buttons. And here we are specifically referring the start button, where we will also set a callback that will associate the start event, because each of the button will have a dedicated callback in order to do something when it will be pushed. And here you can see some features of what you can do in terms of flex, but everything is documented, quite well documented through the LVGL documentation website. Now let's talk about the free object, 1, 2, 3. We create this object providing a specific object width and date, but we also create the start handler that will manage the event of the click and will start the animation. When the user will click the start button, the callback will be automatically called and will start the automation. So let's see what happened here. Basically, there is a timeline that is the time that elapses between one animation and the other. The time is always expressed in terms of milliseconds. We will associate two different callback for each object, one managing the width and one managing the height. And we will have this for object 1, object 2, and object 3. The animation for the object 1 will start at time 0 and will end at time 300. The animation for object 2 will start at 200 and will end at 500. The animation for object 3 will start at 400 and stop at 700. How it is this implemented? This is the timeline creation. So basically here you can see that we are creating the animation for the object 1. There are two callbacks. The one is in charge to control the width of the object, and the other one is in charge to control the height of the object. Whenever the callbacks are called, the width or the height, whatever it is, of the object will be set accordingly in the same way we have seen in the beginning for the animation of the image. Basically, you are supposed to provide a timeline that will manage the range between 0 and whatever is the parameter that you provided with the set value. The set time will provide the range between 0 and whatever to manage all the values within this range. This is for object 1. The same will be repeated for object 2 and 3, just with difference start and stop. So basically, we are saying that object 1 will start at 0, object 2 will start at 200, object 3 will start at 400. And we also define additional two callback for the stop and delete button. The stop button will basically stop the animation, so the animation will freeze basically, and the delete button will simply delete the animation, so nothing else will happen. Now let's move to the sliders. This demo was intended to show how you can recolor. If you remember, we talked about the recolor capability of the images. So basically, here we have the same image. It's never changed, but we are just calling the recolor callback whenever changes censored through the sliders. Let's see the code for this application. We need to create for sure its own panel. In the panel, we will put the red, green, blue, and the opacity slider. Associated to this slider, we have dedicated string. We will set for each slider the possible values, and we will align the slider one respect to the other. So we will first of all put the red slider, and then we will say that the green slider is to its right in the middle, and so on for the blue and for the opacity slider. This create slider function is actually the one that created the slider with the text that we shown. So it created the slider, it created the range for the slider, set the size, the background color, and also the callback associated to the slider. The callback is in charge to provide the value when it's changed. This is what is happening here. Basically, the callback is in charge to get all the values of all the slider, including the one for the opacity, and then call the recolor image API in order to change the appearance of the image in the upper side. Applying this color, you will see that the image is changing. This is more or less cover a good part of the code. For time reason, we cannot go further, but let me spend a few words about the LVGL simulators and the visuals to the visual editors. We implemented the demo and we tested demos using Visual Studio Code. Basically, it's one of the most used editor for code that we have nowadays. But the good thing is that more or less 1 week ago, the LVGL community released the simulator for LVGL framework. Actually, the simulator was already available even before, but 1 week ago they aligned the simulator to the code that we are using. I remember that we are using LVGL 8.3. In the demo, we used actually 8.3.10. That is the head of the stable version of the stable branch of LVGL. And when they updated the simulator, it was 8.0. Now it's 8.3. So you can work in a kind of matching condition. Basically, you can just download the simulator. You can download it from the link that you can see on the bottom of the page, and you can start playing with it. In our case, we added the GUI file, so you can make some minimal changes, but you can get the whole code from the Variscite repository if you want to use it. Keep in mind that the simulator comes with some preset values for the LVGL configuration. I'm referring to the file lv.conf _conf that you can see in kind of orange in the left tab, and also the values of the lv_drv_conf, that is the configuration for the driver. Everything can be found in the repositories because we enabled a lot of features just to create our demo. But feel free to disable. The framework is fully customizable. Keep in mind that it has been designed for microcontrollers, not for MPU. So the target of this framework is to be extremely compact. We tested it with Dart6UL using the frame buffer. We know we tested it also with our MX8M families, and it's working the same. So on this platform, you will not have specific memory constraint compared to MCU, but you can always strip the application down according to your need and just enable whatever you need only. So with the simulator, you can run the application in the same way you will see it running on the target, and can give you a better understanding of what will happen on the target. Just be aware that this is just a simulator, so it's not something like Qt Creator or what you have seen in the WX Widgets webinar, where we show you a graphical editor that was allowing to create the graphical application from, let's say, a graphical point of view. The simulator is just a simulator. You write the code and the simulator can run it. But there's also the chance And this is what happens when you run simulator. Basically, you will see something like this. The same application with the same resolution will run on your PC. But let me spend a few words about the visual tool that LVGL provide. This is a commercial tool where you can design it according to the license. You can just design one widget, but at least you can try to understand how it works. And this is a very nice tool because it's fully graphical, and unfortunately it's not free, but you can start with a trial and then evaluate yourself if it makes sense or not for your application. And this basically closes the presentation. So if you have any question, please feel free. Okay. We have a question about UTF-8 management. Yes, basically this framework manage UTF-8 character set, but it also manage the multi-language support in case you need it. This is a very nice feature because you can create your application without caring too much about the localization, and you can just let's say preset the strings, and then you can populate later according to the localization that you want to apply. Okay. Someone is asking if it is running on bare metal or Linux. Actually, both. This has been designed to run bare metal on the MCU, but it's been recently ported to Linux frame buffer, and it actually runs even on a Windows PC. The simulator that I was talking about basically is a kind of application running in Windows. There are no limitations. There is also for Mac if you like. So feel free to use it. We have a question about layout. Does it support layout? It supports the styles, not strictly the layout, but you can mask actually the widgets one over the other, so you have a kind of management on layout. I don't know if this is what you are actually looking for. Can GPU support be used for acceleration? Okay, good question. Let me clarify that for the SoCs that support GPUs, I'm not talking, this webinar was intended for 6UL, but we tested the framework even on top of the IMX8 family where there is the GPU. We don't strictly test the GPU. Formally, there is a specific configuration where you can use SDL2 and use the acceleration provided through SDL2 library. Now, SDL2 can be used on top of Wayland, which support the GPU acceleration for all the MX8 family. So if your target is using the MX8 family with Wayland, probably you can just add the SDL2 library, and on top of this, configure consistently LVGL to use LVGL library, and then you should be able to get acceleration within LVGL. Okay, let's see if there is any other question. We have a question about IMX93. Yes, basically you can run it also on IMX93. This is not a problem. We tested basically with the frame buffer, and the frame buffer works on any SOM. This is not a limitation. As I say, the SDL tool should work with the GPU for all the GPU-enabled sources. And about the Wayland, basically, it will just be a kind of compositor that will manage the rendering. We have another question about how to initialize the display. Basically, for each specific backend that you're going to use, either the SDL2 or frame buffer or DRM, because there's also the DRM, but we haven't seen a very nice performance with the DRM backend. The documentation provides specific display initialization sequence. So it's just documented in the LVGL web pages, and you can find the reference to the documentation within the presentation. This presentation also will be available in the YouTube channel of Variscite. So you can find it all the link. You can find there all the link. Okay, for the time being, I'm not seeing further questions. So let me close the webinar, just pointing you to our links. You can reach us through the website, variscite.com, through our sales, through the customer portal, and you will find all the documentation about the BSPs, what we provide for each SOM in variswiki.com. And you can find all the code, because we publish everything, we have no lost code, in GitHub Varigit. Thanks for joining. Hope to see you to the next webinar. Bye-bye.